Look up on a clear autumn night, away from the glow of city lights, and you might catch sight of it, a faint smudge of light in the constellation Andromeda. It doesn't look like much from here, this soft blur against the darkness, but that unremarkable patch of light is the Andromeda Galaxy, a spiral city of over 1 trillion stars, each one a sun in its own right, many with their own retinue of worlds spinning through the cosmic dark. Right now, as you read these words, Andromeda is racing toward us at roughly 110 kilometers every second. That's nearly 250,000 miles per hour. In the time it takes you to draw a single breath, Andromeda has closed the distance between our galaxies by more than 300 kilometers. By the time you finish this sentence, it will be over 1,000 kilometers closer than when you began. For most of cosmic history, this collision course has unfolded in silence and darkness, invisible to any observer. The galaxies themselves know nothing of their approach. They simply follow the ancient choreography written into space-time itself billions of years ago, when the universe was young and the first structures were just beginning to coalesce from the primordial dark. But now, in this particular moment in cosmic time, there exist observers on a small blue world who have learned to read the hidden signatures of motion written in starlight. We have measured the impossible, and what we've discovered is both thrilling and humbling in equal measure. Our Milky Way galaxy and the Andromeda galaxy are locked in a gravitational embrace that has been tightening for billions of years. The question that has captivated astronomers for decades is not whether these two massive spirals will interact, but when and how and what will become of us when they do. This is a story about time measured not in years or centuries, but in billions of years. It's a story about distances so vast that light itself, traveling at the ultimate cosmic speed limit, takes 2.5 million years to cross the void between these galaxies. It's a story about forces patient and inexorable, about the strange emptiness of space, about supermassive black holes spiraling toward merger, and about the ultimate transformation that awaits both galaxies when their long approach finally ends. It's also, in a very real sense, a story about fate and uncertainty, about the limits of prediction when dealing with systems of almost incomprehensible complexity. Because, as we'll discover, even the question of whether a collision will happen at all turns out to be more uncertain than scientists thought just a few years ago. Let's begin at the beginning, with a simple question that turns out to have been remarkably difficult to answer. How do you measure the motion of something 2.5 million light years away? The challenge facing astronomers studying Andromeda's trajectory is almost comically difficult. Imagine standing on the surface of the moon and trying to measure how fast a human hair is growing on Earth. That gives you some sense of the precision required to detect the sideways motion of a galaxy millions of light years away. And yet, this is exactly what astronomers needed to do to determine whether we were truly on a collision course. To understand the magnitude of this challenge, consider the numbers. Andromeda is 2.5 million light years away. A light year is about 9.5 trillion kilometers, so we're talking about a distance of roughly 24 quintillion kilometers. That's 24 followed by 18 zeros. At this distance, even if Andromeda were moving sideways at hundreds of kilometers per second, the angular shift in its position would be measured in millionths of an arcsecond per year. An arcsecond is 1/3600th of a degree, and we need to measure a millionth of that. To put this in perspective, 1/millionth of an arcsecond is roughly equivalent to the width of a human hair seen from a distance of about 8,000 kilometers. We're asking our telescopes to measure cosmic motion with a precision that seems to defy common sense. The easy part, relatively speaking, was measuring Andromeda's radial velocity, how fast it's moving directly toward or away from us. This has been known since 1912, when astronomer Vesto Slipher working at Lowell Observatory in Flagstaff, Arizona, observed that the light from Andromeda was blue-shifted. Slipher was a pioneer in measuring the velocities of what were then called spiral nebulae. Using spectroscopy, the technique of splitting light into its component wavelengths, he could measure how those wavelengths were shifted compared to laboratory measurements. Just as the siren of an approaching ambulance sounds higher pitched than one moving away, light from an approaching object gets compressed toward the blue end of the spectrum. This is the Doppler effect, and it works for light just as it does for sound. Andromeda's blue shift was substantial. Slipher measured it approaching at about 300 kilometers per second relative to the Sun, the highest celestial velocity ever measured at that time. But here's where it gets interesting. The Sun itself isn't sitting still. It's orbiting around the Milky Way's center at about 225 kilometers per second. And much of that motion happens to be in Andromeda's direction. When astronomers corrected for the Sun's own motion through the galaxy, they found that Andromeda's approach velocity relative to the Milky Way itself is about 110 kilometers per second. This radial velocity tells us how fast Andromeda is closing the distance, but it tells us nothing about sideways motion. The sideways motion, the proper motion, as astronomers call it, is what determines whether an approaching object will hit you or miss you. A baseball thrown at your head at 90 miles per hour will miss you harmlessly if it's also moving sideways fast enough. Similarly, Andromeda's approach velocity alone couldn't tell astronomers whether we were in for a collision or a near miss. But knowing something is approaching doesn't tell you if it's going to hit you or pass you by. A car racing toward you at highway speeds might still miss you by a wide margin if it's also moving sideways. The critical question was Andromeda's tangential motion, its sideways velocity across our line of sight. This measurement, called proper motion, would reveal whether we were in for a direct hit or a near miss. The problem is that proper motion produces an almost imperceptibly tiny change in position over time, especially for something as distant as Andromeda. The galaxy needed to be observed over many years with extraordinary precision, its position carefully measured against background reference points that were even farther away and therefore appeared stationary. Enter the Hubble Space Telescope. Between 2002 and 2010, Hubble was used to painstakingly measure the positions of thousands of individual stars within Andromeda, comparing their locations against hundreds of distant background galaxies. These background galaxies, billions of light years away, served as a fixed reference frame. Over the course of 8 years, astronomers watched for the almost imperceptible shift in Andromeda's stars against this distant backdrop. The team, led by Roland van der Merel and Sangmo Tony Sohn at the Space Telescope Science Institute, worked with data so precise that they were essentially measuring cosmic motion with the accuracy of a few millionths of a degree. Think of trying to measure an angle smaller than the width of a human hair viewed from a distance of 10 miles. The observations required every bit of Hubble's extraordinary precision and stability. In 2012, after years of analysis, the team announced their findings. Andromeda's sideways motion was negligible, almost exactly zero. This meant that the galaxy wasn't going to pass us by at some safe distance. It was heading nearly straight toward us. The collision, they concluded, was inevitable. The most likely scenario, according to their computer simulations, was a head-on merger occurring in approximately 4 billion years. The announcement sent ripples through the astronomical community and captured the public imagination. Headlines declared our galaxy's doom. Simulations showing the spectacular collision were created, visualizing the chaos that would unfold as 2 of the 3 largest galaxies in our local group of galaxies finally met after their long approach. For more than a decade, this prediction stood as settled science. Astronomy textbooks and popular articles treated the Milky Way-Andromeda collision as a certainty, a fixed point in our galaxy's future. Computer models tracked the merger through its stages, showing how the galaxies would pass through each other, separate, and then return for multiple encounters before finally settling into a single merged galaxy. But science, at its best, is always ready to revise its conclusions in light of new evidence. And in 2025, a new study threw a significant wrench into what had seemed like a certain prediction. Till Sawala of the University of Helsinki, working with colleagues at Durham University in the United Kingdom and the University of Toulouse in France, decided to revisit the collision prediction using the most recent observational data and more sophisticated simulations. Their work, published in the journal Nature Astronomy, incorporated two critical elements that previous studies had either ignored or couldn't account for with earlier data. First, they included the gravitational influence of the Large Magellanic Cloud, a satellite galaxy of the Milky Way that's actually the fourth largest galaxy in our local group. The Large Magellanic Cloud, visible from the southern hemisphere as a fuzzy patch in the night sky, contains perhaps 40 billion stars. While that's small compared to the Milky Way's 300 billion or Andromeda's trillion, it's still substantial enough to have measurable gravitational effects. The key insight is the Large Magellanic Cloud's orbital orientation. It has only about 15% of the Milky Way's mass, but its orbit carries it in a direction roughly perpendicular to the Milky Way-Andromeda approach vector. This means it tugs on the Milky Way in a direction that can perturb our galaxy's trajectory relative to Andromeda. Imagine two cars on a collision course, but one car is being pulled sideways by a third vehicle attached by a cable. That sideways pull can be just enough to change a head-on collision into a near miss. Previous studies had largely ignored the Large Magellanic Cloud's influence, treating the Milky Way-Andromeda system as if it existed in isolation. But the local group is not just two galaxies. It's a complex system of dozens of galaxies, and while most are small, the largest few can have non-negligible effects on the trajectories of the major players. Second, Sawala's team included the Triangulum galaxy, the third largest member of the local group. Triangulum, also called Messier 33, is a smaller spiral galaxy containing perhaps 40 to 60 billion stars. It's located about 3 million light-years from both the Milky Way and Andromeda, forming a rough triangle with the two larger galaxies, hence its name. Earlier studies had suggested that Triangulum might eventually fall into the Milky Way-Andromeda system and participate in a three-way merger. Or it might be ejected from the local group entirely during the chaos, or it might end up orbiting the merged Milky galaxy without merging itself. The uncertainty about Triangulum's fate reflects the chaotic nature of multi-body gravitational systems. With three or more massive objects interacting, outcomes become extraordinarily sensitive to initial conditions. But perhaps most importantly, Sawala's team didn't just run a few simulations based on the most likely values for each variable. They ran more than 100,000 simulations, each one varying the input parameters within their ranges of observational uncertainty. This is a crucial methodological advance. Every measurement in astronomy comes with uncertainty. When we say Andromeda is 2.5 million light-years away, there's actually an error bar on that measurement. When we say it's approaching at 110 kilometers per second radially, that too has uncertainty. The masses of the galaxies, the distance, the velocities in 3 dimensions, the influences of smaller galaxies, all of these have measurement uncertainties. Earlier studies typically used the single most probable value for each parameter and ran a limited number of simulations to explore the general outcome. But Sawala's Monte Carlo approach samples the entire parameter space. Each simulation randomly selects values for all the variables from within their uncertainty ranges. Run this enough times, and you build up a statistical picture not just of the most likely outcome, but of the full distribution of possible outcomes weighted by their probabilities. Think of it like weather forecasting. You can run one simulation with the most likely current conditions and get one prediction. But meteorologists know that uncertainties in initial conditions matter enormously. So they run ensemble forecasts, dozens or hundreds of simulations with slightly different starting points. This gives them a probability distribution for the forecast rather than a single answer. Sawala's team applied the same philosophy to the question of galaxy collision. The results were surprising and humbling. When all the gravitational players were accounted for and all the uncertainties properly explored, the probability of a Milky Way Andromeda collision in the next 10 billion years dropped to approximately 50%. A coin flip. The fate that had seemed certain was now profoundly uncertain. In roughly half of the simulations, the two galaxies experienced at least one close encounter within about 500,000 light-years or less, close enough for a process called dynamical friction to slowly rob energy from their orbits, ensuring an eventual merger, even if it took many billions of years. But in the other half, the galaxies passed at greater distances, too far apart for dynamical friction to work effectively. In these scenarios, the Milky Way and Andromeda might continue their orbital waltz for a very long time indeed, perhaps never merging at all within the lifetime of the universe as we know it. Even the timing, if a merger does occur, shifted in the new analysis. Rather than 4 to 5 billion years, the most likely collision timeframe, if it happens, is now estimated at 7 to 8 billion years from now. This revision might seem like a setback, a failure of prediction, but it's actually science, working exactly as it should. As our observations become more precise and our models more sophisticated, our predictions become more accurate, even if that means acknowledging greater uncertainty. The universe doesn't care about our desire for neat, certain answers. It simply is what it is, playing out according to the laws of physics with all their complexity and chaos. So what we have now is not a certain collision, but a probability, a range of possible futures. In one future, the collision never happens, and the Milky Way and Andromeda remain separate galaxies, perhaps passing within 1 million light-years or so before their mutual gravitational dance carries them apart again. In another future, they experience one or more close encounters before eventually merging into a single galaxy billions of years from now. For the purposes of our journey tonight, we're going to explore what would happen if the collision does occur, not because it's certain, but because understanding this possible future illuminates something profound about how galaxies evolve, how gravity shapes the cosmos, and how the structures we see in the universe came to be. Throughout the universe, we can observe galaxies in various stages of merger, from first approach to final coalescence. What makes the potential Milky Way Andromeda merger special is simply that it's ours, and that it might unfold on a timescale and at a distance that lets us study it with incredible detail. So let's explore this possible future, acknowledging that it's one of two roads our galaxy might travel. The force that would bring these galaxies together, whether the merger happens or not, is the same force that holds you to the surface of the Earth, that keeps the moon in orbit around our planet, that binds the sun and all its worlds together. We tend to think of gravity as a local phenomenon, something that operates over human-scale distances or perhaps solar system-scale distances. Drop a ball and it falls. The Earth orbits the Sunday. These are the familiar manifestations of gravity. But gravity's reach is truly infinite. It never stops, never turns off, never reaches some distance where it simply quits working. It simply gets weaker with distance, falling off according to the famous inverse square law. Double the distance, and gravity's strength drops to 1/4. Triple the distance, and it drops to 1/9, but it never reaches zero. This means that every massive object in the universe exerts a gravitational pull on every other massive object, no matter how distant. You, sitting or lying wherever you are right now, Exert a gravitational pull on Andromeda, and Andromeda pulls on you. The forces are unimaginably tiny, far too small to ever measure or notice. But they exist. They're real. And mathematically speaking, they're non-zero. Between the Milky Way and Andromeda, across 2.5 million light-years of space, gravity has been at work since the universe's earliest moments. The same primordial density fluctuations that caused both galaxies to form in the first place also determined their trajectories through space. They emerged from the Big Bang already on trajectories that would eventually bring them together, or at least closer together. They've been falling toward each other with varying speeds and directions for most of the age of the universe, for over 13 billion years. Think about that for a moment. The gravitational dance between these galaxies began when the universe was young, when the first stars were just beginning to form, long before our sun existed, long before Earth, long before life. The pull between them has been constant and patient, operating without pause across timescales that dwarf human history, that dwarf the entire evolution of life on Earth. But galaxies are not just the visible stars and gas we can see through our telescopes. This is one of the great discoveries of modern astronomy, and one of its great mysteries. Every galaxy is embedded in a vast halo of dark matter, that mysterious substance that makes up most of the matter in the universe, but interacts with ordinary matter only through gravity. It emits no light, absorbs no light, passes through ordinary matter like a ghost. We know it exists only because we can see its gravitational effects. The evidence for dark matter comes from many observations, but one of the most compelling is galaxy rotation curves. Stars and gas in the outer regions of galaxies orbit far faster than they should based on the mass of visible matter alone. The extra gravity needed to keep these outlying regions in their orbits must come from some additional mass we can't see, and that mass is dark matter. The dark matter halo around the Milky Way extends far beyond the visible spiral disk. Our spiral disk of stars, gas, and dust is roughly 100,000 light-years across. But the dark matter halo might extend to 300,000 light-years or more. Andromeda's dark matter halo is similar, or perhaps larger, given Andromeda's somewhat greater mass. And here's the crucial point. It's these dark matter halos that provide most of the gravitational mass pulling the galaxies together. The visible stars and gas that we photograph and admire, the spiral arms and bright cores, these are almost like tracers, visible markers indicating the locations of far more massive concentrations of invisible matter. The stars are the foam on the surface of a deep, dark ocean. When we talk about the Milky Way and Andromeda colliding, we're really talking first and foremost about their dark matter halos interpenetrating and eventually merging. The stellar components, the gas, all of that follows along. But the gravitational scaffolding of the collision is provided by the invisible dark matter. As the galaxies approach and their dark matter halos begin to overlap, something interesting happens. A process called dynamical friction comes into play. Imagine pushing your hand through water. The water resists your motion, slowing you down through friction. Dynamical friction is similar, but instead of water molecules, it's the cloud of stars and dark matter particles in one galaxy's halo that creates drag on the other galaxy. This friction is subtle and slow, but over hundreds of millions or billions of years, it has a profound effect. It gradually robs energy from the galaxy's orbital motion, causing their orbits to decay. Each close passage between the galaxies removes a bit more energy, bringing them closer together for the next encounter. This is why many simulations show the galaxies not merging on their first pass, but instead having multiple encounters. They might sweep past each other, separate to a distance of hundreds of thousands of light years, then slowly fall back together for another pass. With each encounter, dynamical friction takes its toll, and the separation distance decreases. Eventually, if they pass close enough often enough, they lose sufficient energy that they can no longer escape each other's gravity, and the final merger becomes inevitable. There's a fascinating problem in galactic dynamics called the final parsec problem. A parsec is about 3¼ light years, and the problem concerns what happens when two massive objects, like supermassive black holes at the centers of merging galaxies, get within about 1 parsec of each other. At this separation, they've already cleared out most of the nearby stars and matter through gravitational interactions, ejecting them or absorbing them. With less matter around to interact with, dynamical friction becomes much less effective. The problem is that without dynamical friction, the black holes might stall at this separation, orbiting each other essentially forever without getting close enough to merge. For years, this was a genuine puzzle in astrophysics. We could see plenty of merged galaxies with single central black holes, which suggested that mergers do eventually complete. But the physics seemed to say they should get stuck. Recent observations may have helped resolve this puzzle. Pulsar timing arrays, galaxy-sized gravitational wave detectors that use dead stars, called pulsars, as cosmic stopwatches, have detected what appears to be a background hum of gravitational waves. This hum seems to come from hundreds of thousands, perhaps millions, of supermassive black hole pairs throughout the universe, all spiraling toward merger. The detection of this signal suggests that the final parsec problem isn't actually preventing mergers. Something, whether it's interactions with remaining gas and stars, perturbations from a third galaxy, or some other mechanism, is helping these black holes bridge the final gap. But we're getting ahead of ourselves. Before we can worry about black holes merging, we need to understand what happens when the galaxies themselves first meet. If the merger occurs, the timeline unfolds over billions of years, so slowly that no human observer, no matter how long-lived, could perceive the motion without time-lapse photography spanning millennia. But from a cosmic perspective, from the point of view of the universe itself, it would be a violent and spectacular event. Let's trace through what might happen, following the timeline suggested by various simulations and observations of similar galaxy mergers elsewhere in the universe. Right now, today, Andromeda is visible in our sky as that faint smudge of light. It spans about 6 times the width of the full moon in the sky, though only its bright central core is visible to the naked eye. Over the next 2 billion years, as the galaxy continues its approach, it would gradually brighten and grow larger in our sky. The change would be imperceptibly slow on human timescales, but inexorable on cosmic ones. By about 2 billion years from now, Andromeda would be noticeably larger than it appears today, though still distant enough that it wouldn't dominate the sky. Its spiral structure might begin to be visible to the naked eye on very dark nights, though by this time, Earth would no longer be a comfortable place for observers. The sun's luminosity increases slowly but steadily as it ages. Current models suggest that within roughly 1 billion years, give or take a few hundred million, this increased energy output will likely trigger a runaway greenhouse effect on Earth, boiling away the oceans and ending all terrestrial life. So any observers of the approaching Andromeda galaxy would need to be elsewhere, perhaps on worlds orbiting younger stars in our galaxy, or on space habitats, or wherever humanity's descendants might have spread in the billions of years between now and then. Around 3.75 billion years from now, if the merger proceeds, Andromeda would fill a significant portion of the sky, its spiral arms stretched across the darkness like a vast cosmic pinwheel. The gravitational influence between the galaxies would be growing profound, and tidal forces would begin to pull and distort both spiral structures. Tidal forces are differences in gravitational pull across an object. The side of the Milky Way facing Andromeda would feel a stronger pull than the far side. This differential pull would begin to stretch and warp the orderly spiral pattern of both galaxies. Long tidal tails, streamers of stars pulled out by gravitational interaction, would start to form, stretching hundreds of thousands of light years into space. At 3.85 billion years, according to some simulations, the sky would brighten noticeably from the emergence of newly formed stars. When gas clouds from the two galaxies collide, they compress each other. Massive, hot, blue stars would blaze into existence in regions where the galaxy's gas clouds meet, adding a blue glow to the night sky of any surviving worlds. By 3.9 billion years, clouds of ionized gas would fill large portions of the sky. These would be glowing nebulae, lit up by the intense ultraviolet radiation from all those newborn stars. The colors would be stunning, reds and purples and blues, vast cosmic clouds backlit by the fires of stellar birth. At 4 billion years, after the first close passage, both galaxies would be severely warped and stretched. The Milky Way's elegant spiral structure would be disrupted, arms pulled into irregular patterns. Andromeda would be similarly distorted. The two galaxies would begin to separate again after this first encounter, but their fates would be sealed. They wouldn't have enough energy to escape each other permanently. Around 5.1 billion years from now, the cores of both galaxies might be visible as a pair of bright lobes in the sky, two brilliant concentrations of stars marking the hearts of the merging systems. The galaxies would be approaching each other again for a second major passage. Between 5 and 7 billion years from now, multiple encounters would occur. Each passage would further scramble the stellar orbits, pulling stars out of their original paths, flinging some into vast tidal tails stretching into intergalactic space. The orderly rotation of both spiral disks would be progressively transformed into the random, disordered motion characteristic of elliptical galaxies. Finally, around 7 to 8 billion years from now, according to the most recent simulations, the merger would complete. The two galaxies would coalesce into a single system, no longer recognizable as two separate entities. The result would be what astronomers call Milkomeda, or sometimes Milkdromeda, a portmanteau of both galaxy names. This new galaxy would likely be a giant elliptical, a roughly football-shaped or spherical collection of stars with no remaining spiral structure, no grand swirling arms, just a smooth, roughly symmetric distribution of stellar light. The timescale is almost incomprehensible to us. We're talking about an event that would unfold over a period longer than half the current age of the universe. The merger would take far longer than the time that's elapsed since the extinction of the dinosaurs, longer than life has existed on Earth, longer even than the Earth itself has existed. From first distortion to final coalescence, the Milky Way-Andromeda merger would be one of the slowest dramas in nature, and yet, paradoxically, it would also be violent, beyond imagining. When we talk about galaxies colliding, it's natural to imagine stars crashing into each other like cars in a massive pileup. But the reality is far stranger, and, in some ways, far more gentle. The key to understanding this lies in grasping just how empty space actually is. We talk about galaxies containing hundreds of billions of stars, and that's true, but those stars are separated by almost inconceivable distances. Space, even within a galaxy, is almost entirely empty. Consider our nearest stellar neighbor, Proxima Centauri. It's about 4.2 light-years away. A light-year is the distance light travels in 1 year, roughly 9.5 trillion kilometers. So, Proxima Centauri is about 40 trillion kilometers away. That's such a large number that it's essentially meaningless to human intuition. Let's try to visualize it with a scale model. If we shrunk the sun down to the size of a ping-pong ball, about 4 centimeters across, then on this scale, Earth would be a tiny grain, about 1 millimeter across, orbiting at a distance of about 4.5 meters. The entire solar system, out to the orbit of Neptune, would fit within about 200 meters. And Proxima Centauri, the nearest star? On this scale, it would be another ping-pong ball located about 1,100 kilometers away. That's about the distance from New York to Miami, or from London to Rome. Imagine one ping-pong ball in New York and another in Miami, with almost nothing but empty space between them. That's the actual density of stars in our galactic neighborhood. Near the centers of galaxies, stars are packed somewhat more densely, perhaps only a few light years apart, rather than the 4+ light years that separate us from Proxima Centauri. But even in those denser regions, the average distance between stars might be equivalent to one ping pong ball every 3 kilometers or so in our scale model. Now imagine two collections of ping pong balls, one scattered across the entire United States and another scattered across all of Europe. And then imagine these two collections passing through each other. What's the chance that any two ping pong balls would actually collide? It's astronomically small, almost zero. This is the reality of galaxy mergers. When the Milky Way and Andromeda interpenetrate, virtually none of the stars will actually collide. They'll pass by each other with room to spare. An observer on a planet orbiting a star in one galaxy would see stars from the other galaxy, gradually filling more and more of the sky, more stars becoming visible, the night sky becoming richer and more crowded with stellar light. But the chance of a close encounter with another star, let alone a direct collision, would be negligible. There's a beautiful irony here. What we call galaxy collisions are actually events where almost nothing collides. It's a collision in the gravitational sense, in the sense that two massive systems interpenetrate and merge. But at the stellar scale, it's more like two swarms of gnats flying through each other. Individual particles almost never meet. And yet, even though stars don't collide, they can't remain unaffected. Some would be accelerated to high speeds and ejected entirely from the merging system, cast out into the darkness of intergalactic space. Others would have their orbits radically altered, stars that once circled serenely in the Milky Way's disk, finding themselves on elongated elliptical orbits that take them far above and below the galactic plane. Still others might end up on orbits closer to the new galaxy's center, crowded into the dense core of Milky. But the Sun and its family of planets, if they still exist at this point, would almost certainly survive intact. Our solar system, bound together by the Sun's gravity, is like a small, tightly bound island. The gravitational perturbations from passing stars, while real, wouldn't be strong enough to tear the planets from their orbits around the Sunday. The system as a whole might be flung to a new location within the merging galaxy, but it would remain a system. So what would happen to our solar system during the merger? Where would we, or more accurately, where would the cold, dead husk of our world and the dimming ember of our aging sun end up? This is one of those questions where we have to embrace profound uncertainty. The motion of any individual star during a galaxy merger is effectively chaotic in the mathematical sense. Tiny differences in initial conditions, differences too small to ever measure, can lead to wildly different outcomes. So we can't predict exactly what would happen to our solar system. We can only speak in probabilities. There's one thing we can say with certainty. By the time the merger occurs, Earth will no longer be habitable and may not even exist in any form we'd recognize. The sun is gradually brightening as it ages, as the nuclear fusion in its core slowly changes its internal structure. In roughly 1,000 million years, give or take a few hundred million, this increased luminosity will pump enough extra energy into Earth's atmosphere to trigger a runaway greenhouse effect. The oceans will evaporate. Water vapor is itself a greenhouse gas, so this will accelerate the heating. Eventually, Earth's surface temperature will soar to hundreds of degrees. The planet will become a hellish, Venus-like world, completely sterile and hostile to any form of life we know. This will happen eons before the galaxy merger even begins. So any life that originated on Earth will either be long extinct or will have left Earth for other worlds. The merger itself, then, would be a concern only for whatever descendants of Earth life, if any, exist in those remote times, living on other planets or in artificial habitats scattered throughout the galaxy. But let's follow the fate of the solar system itself. Earth and Sun, and all the other worlds bound to our star. When the galaxies merge, what becomes of this particular collection of matter that has been orbiting together for over 4.5 billion years? The best predictions we have come from detailed computer simulations. These simulations follow the positions and velocities of millions of particles representing stars as the galaxies merge, allowing astronomers to build up statistical predictions even if they can't predict any individual star's fate. According to these simulations, there's roughly a 50% chance that the solar system will be flung outward to about 3 times its current distance from the galactic center. Right now, we orbit about 26,000 light-years from the Milky Way's center, out in a relatively sparse region between major spiral arms. 3 times farther out would place us at perhaps 75,000 or 80,000 light-years from the center of Andromeda, well into the outer reaches of the new galaxy's halo. The night sky from such a location would be dramatically different from what we see today. Right now, the Milky Way appears as a band of light across the sky, the combined glow of billions of stars in the galactic disk, seen edge-on from our position within it. From a location far out in Andromeda's halo, the galaxy would instead appear as a large, bright, roughly spherical glow occupying a sizable portion of the sky. The stars in the night sky would be sparser than they are now, the nearest stars farther away on average. There's also a roughly 12% chance, according to some simulations, that the solar system could be completely ejected from the newly formed galaxy. This might sound catastrophic, but it actually wouldn't affect life on any planets in the solar system at all. At least, not directly. We don't rely on other stars for anything essential. The sun provides all the energy and light we need. The night sky from such a location would be extraordinary. Instead of a sky full of individual stars, observers would see several large, glowing clouds. These would be distant galaxies, including perhaps Andromeda itself, now an external object rather than something we're embedded within. The Triangulum galaxy might be visible, and the various smaller satellite galaxies of the local group. The sky would be full of galaxies but empty of stars, a perspective utterly unlike anything visible from any planet in the universe today. There's a third possibility, smaller in probability but dramatic. Some simulations show scenarios where the solar system could be drawn inward toward the dense central regions of the merging galaxy. In the most extreme cases, the sun could pass relatively close to the central supermassive black hole or black holes. If the sun passed very close to a supermassive black hole, tidal forces could potentially become strong enough to tear it apart, stretching the star into a long stream of stellar matter that would fall into the black hole over time, creating a brief but spectacular flare of radiation as the matter heated to millions of degrees before vanishing past the event horizon. But the chances of this are very small. Space is simply too vast, and even the cores of galaxies, dense as they are by galactic standards, are still mostly empty. The most likely outcome is the first one. The solar system, wherever it ends up, will remain intact. The planets will continue to orbit the sun, moons will continue to orbit their planets. The architecture of our little corner of space would survive the chaos of the merger. We would just be in a different neighborhood when it's all over. It's worth pausing to appreciate what this tells us about the structure of space and the nature of gravitational binding. The solar system is a tiny, tightly bound island of order, held together by the sun's gravity. The forces within the solar system, the gravitational bonds between the sun and its planets, are vastly stronger than the average gravitational forces acting between stars in a galaxy. So even when the galaxy around us is being torn apart and reformed, our local neighborhood remains stable. This is true for every star system in both galaxies. Each star and its attending worlds is a small fortress of stability in the larger chaos. The merger reshuffles where these fortresses are located and how they move, but it doesn't destroy them. And yet, while the stars themselves mostly avoid colliding, there's one component of galaxies that cannot avoid colliding: Between the stars of every galaxy, there exists a diffuse medium of gas, mostly hydrogen and helium left over from the Big Bang, along with heavier elements forged in stars and scattered into space by supernova explosions. This interstellar medium, as it's called, is organized into vast clouds, structures that can span hundreds or thousands of light years. Some of these clouds are cold and dense by astronomical standards, perhaps -200 degrees Celsius, and containing a few hundred atoms per cubic centimeter. That's still a better vacuum than we can achieve in any laboratory on Earth, but it's dense compared to the even more rarefied gas between the clouds. Other clouds are hot and tenuous, heated to millions of degrees by supernovae and stellar winds. So hot that individual atoms are stripped of their electrons, creating a plasma that glows faintly in X-rays. In spiral galaxies like the Milky Way and Andromeda, much of this gas is concentrated in the spiral arms, where it serves as the raw material for new star formation. The spiral arms aren't just where the stars are. They're regions of enhanced density, cosmic traffic jams where stars and gas clouds bunch up due to density waves propagating through the galactic disk. In these denser regions, the gas clouds can become unstable under their own gravity and begin to collapse, fragmenting into smaller clumps that eventually become stars. Unlike stars, these gas clouds are large and diffuse enough that they cannot simply pass through each other. When gas clouds from two merging galaxies meet, they collide in a very real sense. The atoms slam into each other, and while any individual atom's collision is a quantum event occurring on timescales of femtoseconds, the collective effect of trillions upon trillions of atoms colliding is to convert the kinetic energy of the cloud's motion into heat and to compress the gas. This compression is exactly what's needed to trigger gravitational collapse and star formation. In a normal galaxy, star formation proceeds at a relatively sedate pace. Dense regions in gas clouds gradually accumulate more gas, growing denser under their own gravity. Eventually, a region becomes so dense and its self-gravity so strong that it collapses catastrophically, heating up in the center until nuclear fusion ignites and a star is born. The whole process is almost stately, taking millions of years from the first hint of a collapsing region to the birth of a star. But in a merging galaxy, star formation explodes into overdrive. We call this a starburst, and the name captures the suddenness and violence of the process. Everywhere that gas clouds from the two galaxies collide, pockets of gas are compressed rapidly and far beyond what would happen in a quiescent galaxy. These compressed regions can't support themselves against gravity. They collapse quickly, and stars form in great profusion. Not just individual stars, but entire clusters of stars, born together from the same parent cloud. The star formation rate, the mass of gas being converted into stars per year, can increase by factors of 10, 100, even 1,000 compared to normal. The Milky Way currently forms about 2 or 3 solar masses worth of new stars per year. That's 2 or 3 stars with the mass of our Sun, though of course many stars are smaller and some are much larger, so the actual number of stars formed per year is different. But in a starburst galaxy, the star formation rate can reach hundreds or even thousands of solar masses per year. We can see this process in action in merging galaxies throughout the universe. One of the best studied examples is the antennae galaxies, 2 spirals currently in the midst of a merger about 60 million light-years away in the constellation Corvus. They're called the antennae because long tidal tails streaming from the galaxies resemble an insect's antennae. These tails are made of stars that have been pulled out of the original galaxies by tidal forces during their encounter. Images of the antennae galaxies reveal brilliant blue knots of star formation scattered throughout the merging system. These knots are vast star-forming regions, each one containing thousands or millions of newly born stars. The blue color tells us these stars are hot and massive, many times the mass of our Sun, burning their nuclear fuel at prodigious rates. Such stars live fast and die young, exhausting their fuel in just a few million years rather than the billions of years that smaller stars enjoy. Infrared observations reveal even more star formation hidden behind dust clouds. The newborn stars pump out intense ultraviolet radiation. When this radiation strikes dust grains in the surrounding clouds, the grains heat up and re-emit the energy as infrared light. So, infrared observations can see through the dust and reveal star formation that's completely invisible in optical light. In the antennae, the total star formation rate is estimated at several tens of solar masses per year, perhaps approaching 100 in the most active regions. The stars born in these starbursts tend to be disproportionately massive. The most common stars formed are red dwarfs, stars with a small fraction of the sun's mass that will burn their fuel miserly for trillions of years. But in starbursts, the conditions favor the formation of more massive stars. The dense, compressed gas clouds fragment into larger clumps on average, and these give birth to heavier stars. These massive stars, while spectacular, are also ephemeral. A star with 10 times the mass of the Sun lives only about 20 million years. A star with 50 solar masses might live just a few million years. They burn through their nuclear fuel at rates that increase much faster than linearly with mass. And when they exhaust their fuel, they don't fade gently. They explode as supernovae, blasting themselves apart in eruptions that can briefly outshine entire galaxies. The result is a brief, by cosmic standards, period of intense activity. The merging galaxy blazes with the light of countless young, hot, blue stars. Supernovae flash across the system like cosmic fireworks. Gas is heated to millions of degrees by supernova shockwaves and by the intense radiation from the young stars. The interstellar medium becomes turbulent and chaotic. But this phase can't last. Star formation requires cold, dense gas that can collapse gravitationally. The starburst uses up this gas rapidly, converting it into stars. Meanwhile, the energy pumped into the remaining gas by supernovae and stellar radiation heats it to temperatures where it can no longer collapse. Some of the gas is ejected entirely from the galaxy by powerful galactic winds, driven by the collective output of millions of stars and supernovae. By the time the merger completes, most of the gas is gone, either locked up in stars or heated and dispersed. And this is exactly what we see in elliptical galaxies, which are thought to be the products of major mergers. Ellipticals have very little cold gas, very little ongoing star formation. They're populated almost entirely by older stars, giving them a distinctly yellow or reddish color compared to the blue-white of spiral galaxies with their ongoing star formation. The Milky Way-Andromeda merger would follow this same pattern, but with one important caveat. Both the Milky Way and Andromeda are mature galaxies that have already converted most of their gas into stars over their long lifetimes. Neither galaxy has enormous reserves of star-forming gas remaining. So, while there would certainly be a starburst during the merger, it might be somewhat weaker than the spectacular displays we see in mergers of younger, more gas-rich galaxies. Still, even a relatively weak starburst by cosmic standards would be an extraordinary event. Billions of new stars would be born over a period of perhaps a few 100 million years. For any observers in the merging system, the sky would be filled with brilliant blue star clusters, glowing nebulae, and the occasional flash of supernovae. It would be a sky of unparalleled richness and drama. There's another possible consequence of all this, gas falling toward the center of the merging galaxy. If enough gas makes it to the very center, it could feed the supermassive black holes that reside there. Gas falling into a black hole doesn't just disappear quietly. It first forms a swirling accretion disk, a rapidly rotating disk of matter spiraling inward. Friction within the disk heats the gas to millions of degrees, making it radiate intensely across the electromagnetic spectrum. If enough material falls toward the black holes during the merger, the result could be a quasar, one of the most luminous objects in the universe. A quasar can briefly outshine the entire galaxy that hosts it, radiating the energy of trillions of suns from a region smaller than our solar system. Quasars were common in the early universe when galaxy mergers were more frequent, but they're rare in the nearby universe today. The Milky Way Andromeda merger might, just might, create one last quasar, a brief return to the violent era of the universe's youth. Or it might not. Whether a merger produces a quasar depends on how efficiently gas can be funneled to the center, and that depends on details that are hard to predict. But even without a quasar, the merger would reshape both galaxies utterly. The transformation from spiral to elliptical is one of the most profound metamorphoses in nature. These two galaxy types look nothing alike, and their differences go far deeper than mere appearance. They represent fundamentally different states of galactic organization, different solutions to the equations that govern how stars move under gravity. Spirals are flat disks with elegant, curving arms, often with a bar structure running through the center, a rectangular concentration of stars that acts like a cosmic conveyor belt, funneling gas toward the center where it can fuel star formation and feed the central black hole. Spiral arms themselves aren't fixed structures, but density waves, regions where stars and gas bunch up temporarily as they orbit, like cars bunching up in a traffic slowdown. Individual stars drift in and out of spiral arms as they complete their orbits, but the arms themselves persist, slowly rotating around the galactic center at a different speed than the stars. Spiral galaxies are actively forming stars, especially in their spiral arms where gas is compressed as it passes through the density wave. They're blue, at least in their disks, because blue light comes from young, hot, massive stars, and these are constantly being born in the arms. They rotate, with stars and gas clouds orbiting the galactic center in roughly circular paths, all going the same direction, creating a grand cosmic carousel that takes hundreds of millions of years to complete a single rotation. Ellipticals, by contrast, are three-dimensional, somewhat football-shaped or spherical, ranging from nearly spherical to quite elongated. They have no disk, no spiral arms, no grand pattern visible in their structure. If you look at an elliptical galaxy, what you see is just a smooth, featureless glow of starlight, brightest at the center and fading gradually toward the edges. The distribution of light follows a mathematical profile, smooth and symmetric, with no hint of the intricate structure visible in spirals. They're not forming stars at any significant rate. The gas that would fuel star formation has been either used up or heated to temperatures too high to collapse and form new stars. They're red or yellow, because their stellar populations are old, without ongoing star formation to replace the massive blue stars that die quickly. Ellipticals are dominated by longer-lived stars that appear yellow or red. The most massive stars have all died long ago. What remains are the smaller, cooler stars that can burn for billions of years, and they don't rotate in any organized way. Oh, elliptical galaxies do have some net rotation, some overall spin, but it's weak compared to spirals. If you measure the velocities of stars in an elliptical, you find they're moving in all different directions. Some stars orbit one way, some the opposite way. Some plunge through the center on highly elongated orbits. Some circle the outskirts on more circular paths. It's organized chaos, a complex three-dimensional web of orbits with no preferred plane, no coordinated motion, nothing like the orderly rotation of a spiral's disk. How does the merger accomplish this transformation? The answer lies in what physicists call violent relaxation, a somewhat paradoxical term that describes a process where the ordered motion of stars in rotating disks is converted into random motion through a violent but brief phase of rapid gravitational changes. Imagine the two galaxies in their first close approach. The Milky Way's stars are orbiting the galactic center in roughly circular paths in the plane of the disk, all going the same direction around the center. Andromeda's stars are doing the same, but in Andromeda's coordinate system, in Andromeda's disk plane, as the galaxies approach, each star feels the gravitational pull not just of its home galaxy, but increasingly of the other galaxy too. During the close passage, which might last only a few 100 million years, the gravitational potential around each star changes dramatically. A star on one side of the Milky Way might be pulled strongly toward Andromeda during close approach. Then, as the galaxies separate, the pull weakens. During the next encounter, the star might find itself on the opposite side and experience a pull in a different direction. These varying forces perturb the star's orbits. A star that was on a nice circular orbit in the Milky Way's disk might get tugged onto an elongated elliptical orbit that takes it far above the disk plane. Another star might be accelerated, gaining energy and moving to a larger orbit. The changes are different for every star, depending on where it is during each close passage and how the gravitational forces play out. Over multiple encounters, as the galaxies pass through each other again and again, each star's orbit is repeatedly perturbed. The cumulative effect is to completely scramble the original orbital structure. What starts as an ordered system, where all the stars are moving in roughly the same direction in a flat disk, becomes a disordered system where stars are moving in every possible direction on a wide variety of different orbits. But here's the key. While the directions are scrambled, the speeds on average stay the same. Energy is conserved. The stars end up moving just as fast as they were before, but now they're moving in random directions rather than all going the same way. The organized kinetic energy of rotation has been converted into random kinetic energy, what physicists call velocity dispersion. This random motion is what puffs the galaxy up into an elliptical shape. Without a preferred direction of motion, there's no reason for the stars to stay in a thin disk. They spread out to fill a three-dimensional volume. The galaxy transforms from a pancake into a football. The mathematics of this process is complex, involving what's called the collisionless Boltzmann equation, a formidable piece of mathematical physics that describes how systems of particles move under mutual gravity without actually colliding. Remember, the stars themselves almost never collide. This is entirely a gravitational process. Stars responding to the changing gravitational field created by the collective mass of all the other stars. This transformation is irreversible, at least on any timescale shorter than many times the current age of the universe. You can't unscramble the egg. The original spiral structure, the beautiful arms and bars and organized rotation are destroyed in the merger and can never be recovered. Entropy, in a sense, has increased. The system has gone from an ordered state to a disordered state, and the second law of thermodynamics tells us that such transitions don't spontaneously reverse. Could a new spiral galaxy form from scratch? In principle, yes, if there were a large supply of cold gas falling into the system from outside. This gas, not having been through the violent relaxation process, could settle into a new disk and potentially form new spiral arms. But as we've discussed, the merger uses up and disperses most of the available gas. What remains is too hot and spread out to condense into a new disk. The gas exists as a hot, rarefied halo around the galaxy, radiating away its thermal energy slowly over billions of years, but never cooling enough to collapse and form new structures. So Milky would almost certainly be an elliptical galaxy. Simulations suggest it would be a giant elliptical, one of the larger such galaxies in the nearby universe. It would contain roughly 1.5 trillion stars, the combined population of both parent galaxies, possibly minus whatever stars were flung into intergalactic space during the merger. Interestingly, Milky would likely be a somewhat unusual elliptical. Most giant ellipticals are extremely dense at their centers, with steep increases in stellar density as you move inward. But simulations of the Milky Way-Andromeda merger suggest the resulting galaxy would have a less dense center than typical, more of a core than a sharp cusp. This might be because both parent galaxies are relatively low density at their centers compared to some galaxies, or it might be a consequence of the specific dynamics of this particular merger. There's also a possibility, depending on how much gas remains in both galaxies at the time of merger, that the result could be something other than a pure elliptical. If substantial amounts of gas remain, and that gas can somehow avoid being used up in the starburst, it might settle into a disk again after the merger, potentially forming a lenticular galaxy, a galaxy that has a disk but no spiral arms. Or it might form what's called a super-spiral galaxy, an unusually large spiral. But these outcomes seem less likely given the current state of both galaxies. Whatever its exact form, Milky would be a massive galaxy, one of the largest in our cosmic neighborhood, and at its heart would be something extraordinary, a binary pair of supermassive black holes spiraling toward their own eventual merger. Every large galaxy appears to harbor a supermassive black hole at its center. These are not the stellar mass black holes formed when massive stars collapse, though those are impressive enough. Supermassive black holes have masses millions or even billions of times that of the Sunday. They lurk at the centers of galaxies, holding court over the dense stellar populations of galactic cores. The Milky Way's supermassive black hole, called Sagittarius A star, has a mass of roughly 4.1 million times that of the Sunday. We know it's there not because we can see it directly. Black holes, by definition, emit no light, but because we can see its gravitational effects on nearby stars. Astronomers have watched individual stars orbit this invisible mass, sometimes whipping around it at speeds of several percent of the speed of light, their motions precisely tracing out elliptical orbits around a point of enormous gravitational pull. Andromeda also has a supermassive black hole at its center, though its exact mass is less certain. Estimates generally place it somewhere between 30 million and 230 million solar masses, significantly larger than our own. When the galaxies merge, these two supermassive black holes would eventually meet, but their journey to union would be long and complex, a process that could take hundreds of millions of years even after the galaxies themselves have merged. Initially, when the galaxies first pass through each other, the black holes would simply fly past each other, embedded in their respective galactic cores. But as the galaxies fall back together and begin their final merger, the black holes would gradually spiral toward the center of the combined system. This inward spiral happens because of dynamical friction, the same process we discussed earlier in the context of the galaxies themselves. As each black hole moves through the sea of stars in the merging galaxy, its enormous gravitational field pulls on nearby stars, accelerating them. By Newton's third law, this means the stars pull back on the black hole, slowing it down. This gravitational drag causes the black hole to lose orbital energy and fall toward the center of the system. Eventually, both black holes would settle into orbits around the common center of mass of Milky. But they would be moving through a very dense stellar environment, the core of the newly formed elliptical galaxy, packed with billions of stars. Continued dynamical friction would bring them closer and closer together. As they approach each other, something fascinating happens. The black holes begin to scatter stars that pass near them. When a star approaches the black hole binary on one side, it can steal energy from the binary's orbital motion and get flung away at high speed. This is called a gravitational slingshot, and it's the same process that we use to send spacecraft on trajectories to the outer solar system. Each star that gets slingshot away carries off a bit of the binary's orbital energy, causing the black holes to move closer together. Over millions of years, countless stars would be scattered in this way, and the black holes would spiral inward. But there's a problem. This process is self-limiting. As the black holes scatter stars, they clear out a region around themselves. The stars nearby get ejected, and what's left is a relatively star-free zone. With fewer stars to interact with, the efficiency of dynamical friction drops. This is the final parsec problem we mentioned earlier. For many years, it wasn't clear how supermassive black hole binaries could overcome this hurdle. But recent observations suggest they do. Somehow, perhaps gas flowing into the galactic center provides additional friction. Perhaps perturbations from asymmetries in the surrounding stellar distribution keep feeding stars into the region where they can interact with the binary. Perhaps in some cases, a third supermassive black hole from another merging galaxy arrives and perturbs the system. Whatever the mechanism, black holes do seem to merge in the end. As the black holes get within a light year or so of each other, a new force comes into play: gravitational radiation. According to Einstein's general theory of relativity, any accelerating mass produces ripples in space-time itself, gravitational waves that propagate outward at the speed of light. For most systems, this effect is extraordinarily weak, but for two supermassive black holes orbiting each other, it becomes significant. Gravitational waves carry energy away from the system, just like light waves carry energy away from a hot object. As the black holes emit gravitational waves, they lose orbital energy. This causes them to spiral closer together, which makes them orbit faster, which makes them emit stronger gravitational waves, which makes them lose energy faster. It's a runaway process, a feedback loop that accelerates as it progresses. The gravitational waves from the early stages of this spiral, when the black holes are still light years apart and taking thousands or millions of years to orbit each other, are far too long wavelength to be detected by instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is designed to detect waves from stellar mass black holes and neutron stars merging, events that produce gravitational waves with frequencies of tens to thousands of hertz cycles per second. The waves oscillate rapidly, compressing and stretching space hundreds or thousands of times per second. But supermassive black hole binaries separated by light years are moving slowly, orbiting each other perhaps once every few thousand years or even longer. The gravitational waves they produce have frequencies measured in nanohertz, billionths of a hertz. One cycle might take years or even decades to complete. These waves have wavelengths of light years, far too long for ground-based detectors to sense. However, these waves can be detected by pulsar timing arrays, one of the most ingenious and beautiful instruments in all of astronomy. It's worth understanding how this works, because it represents a triumph of human creativity in finding ways to observe phenomena that seem impossibly subtle. Pulsars are rapidly rotating neutron stars, the ultra-dense remnants of supernova explosions. When a massive star explodes, its core collapses to incredible densities, compressing about 1.5 times the mass of the Sun into a sphere only about 20 kilometers across. That's the density of an atomic nucleus, but sustained across an entire stellar remnant. A teaspoon of neutron star material would weigh billions of tons. Neutron stars have intense magnetic fields, trillions of times stronger than Earth's magnetic field. These fields channel charged particles into beams that emit radio waves from the magnetic poles. As the neutron star rotates, these beams sweep across space like lighthouse beacons. If a beam happens to point toward Earth during the rotation, we receive a pulse of radio waves, hence the name pulsar, a pulsing star. Some pulsars are extraordinarily stable rotators. They spin dozens or even hundreds of times per second, and they maintain this rotation rate with remarkable precision. The most stable ones, called millisecond pulsars, tick away with regularity that rivals the best atomic clocks humans have ever built. Some pulsars maintain their rotation period stable to 15 or more decimal places over years of observations. Now, Here's the clever part. The pulses from a pulsar arrive at Earth with predictable timing. If you know the pulsar's rotation period precisely, you can predict exactly when each pulse should arrive. Any deviation from the predicted arrival time tells you that something has changed, either the distance to the pulsar or the properties of space-time between us and the pulsar. Gravitational waves passing through our region of space would do exactly that. As a gravitational wave goes by, it alternately compresses and stretches space. When space is compressed in the direction of a pulsar, the effective distance to that pulsar decreases slightly, and pulses arrive a tiny bit earlier than expected. When space is stretched, the distance increases and pulses arrive late. The effect is incredibly small. Even for the most powerful gravitational waves from nearby supermassive black hole binaries, the timing shift would be only microseconds or less. But millisecond pulsars can be timed with precision better than a microsecond. But there's a complication. Many things can affect pulsar timing. The pulsar itself might have tiny variations in its rotation period. Our clocks might have errors. Interstellar space isn't perfectly empty. Radio waves traveling through the ionized gas between stars are slowed slightly, and this slowing varies as the amount of intervening gas changes. The Earth's position relative to the solar system's center of mass changes as the planets orbit, and we have to account for this. Dozens of effects can create timing variations. The solution is to observe many pulsars spread across the sky simultaneously. Random effects affecting individual pulsars will be uncorrelated. Each pulsar will show its own random timing jitter. But gravitational waves affect spacetime itself, and spacetime is what all the pulsars are embedded in. A gravitational wave passing through the solar system will create a correlated pattern of timing shifts across all pulsars, a pattern that depends on each pulsar's direction in the sky and the properties of the gravitational wave. This is a pulsar timing array, a collection of pulsars observed regularly and precisely, their combined timing data analyzed to search for the subtle, correlated patterns that would indicate gravitational waves. The North American Nanohertz Observatory for Gravitational Waves, NanoGrav, monitors dozens of millisecond pulsars scattered across the sky, observing them roughly weekly with large radio telescopes. Similar collaborations exist in Europe, Australia, India, and China. Together, these pulsar timing arrays form a galaxy-sized gravitational wave detector. The size is important. LIGO's arms are 4 kilometers long. That limits it to detecting waves with wavelengths of kilometers to thousands of kilometers. A pulsar timing array, by contrast, uses the changing distance between Earth and pulsars as its detector arms. Since the pulsars are hundreds or thousands of light years away, the effective arm length is measured in light years. This allows detection of much longer wavelength gravitational waves, waves with periods of months to years to decades. In 2023, several pulsar timing array collaborations, including NanoGrav in North America, announced the detection of a background hum of gravitational waves at nanohertz frequencies. This wasn't a signal from an individual black hole binary, but rather a stochastic background, the combined effect of countless supermassive black hole binaries throughout the universe, all at various stages of their inspiral. Their individual signals overlap and add together to create a sort of cosmic background noise of gravitational waves, analogous to how individual voices in a crowded room blend into a general hubbub of sound. This detection is profound. It tells us that supermassive black holes do merge, that the final parsec problem is solved one way or another, and it gives us a preview of what the Milky Way and Andromeda's black holes might do billions of years from now, adding their own contribution to the universe's gravitational wave background. As the Milky black holes spiral closer, the gravitational waves would get stronger and their frequency would increase. Eventually, over a period of millions of years, they would approach within the final few light years. The inspiral would accelerate. Within the last 100,000 years before merger, they would go from light years apart to light months apart. In the last 1,000 years, from light months to light weeks. In the final year, from light weeks to light days, and then, in a final rush, over the last few hours or days, the black holes would spiral together impossibly fast, orbiting each other hundreds or thousands of times per second despite their enormous masses. The gravitational waves at this point would be carrying away energy equivalent to the mass energy of entire stars every second. Space-time around the black holes would be warping and writhing in ways that strain our ability to visualize. Finally, the event horizons would touch and merge. The two black holes would become one. The merger itself would release a final burst of gravitational waves, the most intense in the entire process. These waves, unfortunately, would still be too low frequency for LIGO, which is designed for stellar mass black holes, and too high frequency for pulsar timing arrays. They'd fall into a gap in our current observational capabilities. Future space-based detectors, like the planned LISA mission, might be able to detect similar mergers of supermassive black holes in distant galaxies. But the local merger, if it happens, would occur far in the future, beyond the reach of humanity. The merged black hole would be truly massive, somewhere between 34 million and 234 million solar masses, depending on Andromeda's black hole's true mass, plus the 4.1 million from the Milky Way's black hole. It would sit at the heart of Andromeda, the gravitational anchor around which 1.5 trillion stars orbit. If any gas falls into this black hole in the aftermath of the merger, the result could be a spectacular display, a quasar or active galactic nucleus shining across the universe. The accretion disk around the black hole would glow with the light of hundreds of billions of stars, and jets of material might be launched from near the black hole's poles at speeds close to that of light, shooting outward for hundreds of thousands of light years. But eventually, the gas would be exhausted or cleared away, and the black hole would go dormant, invisible, except for its gravitational influence. It would simply sit there, waiting, as black holes do, patient as the universe itself. The story of the Milky Way-Andromeda merger, if it happens, is really a story about scales, about distances, and times so vast they challenge our comprehension. It's about gravity, the weakest of the fundamental forces on the quantum scale, but the sculptor of the universe on the largest scales, patient and inexorable. It's about chaos and order, about how the elegant structure of spiral galaxies can be transformed into the seeming disorder of ellipticals, which is itself a kind of order, just more complex. But perhaps most of all, it's a story about perspective. From a human perspective, from the timescale of a single life, or even the timescale of human civilization, the galaxy seems eternal and unchanging. The stars in their courses, the great wheel of the Milky Way arcing across the night sky, these seem like permanent fixtures of the cosmos. The idea that all this could change, that our galaxy could merge with another and be transformed into something completely different, seems almost inconceivable. But from the perspective of the cosmos itself, galaxies are young and dynamic. They form, they grow, they merge, they evolve. The Milky Way we see today is itself the product of countless mergers with smaller galaxies over cosmic time. We know this because we can see the debris streams, tidal tails from dwarf galaxies that merged with us in the past, their stars now scattered throughout our galactic halo. The Sagittarius dwarf elliptical galaxy is merging with the Milky Way right now, being slowly torn apart and absorbed. In a cosmic sense, galaxy mergers are not rare catastrophes, but the normal process of galactic evolution. Throughout the universe, we can see galaxies in various stages of merger. We see pairs just beginning their approach, still recognizable as two separate spirals, but with tidal tails already forming. We see galaxies in mid-merger, their structures severely disrupted, cores approaching, starbursts blazing, We see recently merged galaxies, the merger complete but the system still settling, turbulent and asymmetric. And we see ancient ellipticals, galaxies that likely formed from major mergers billions of years ago, now quiet and red and peaceful. The potential Milky Way Andromeda merger is special to us because it's ours, because it involves our home galaxy. But in the grand scheme of cosmic evolution, it's just one more merger in a universe full of them. It's special also because of its timing. Because the 50% probability of merger means we live in an interesting moment, a moment of uncertainty about our galaxy's far future. If the merger happens, it will unfold over a timescale longer than multicellular life has existed on Earth. From first distortion to final coalescence. From the moment the galaxy's tidal interactions begin to significantly affect their structure to the moment Milky finally settles into its equilibrium form, vast eons will pass. Stars like our Sun will be born, live their entire main sequence lifetimes, and die, all within the span of the merger. Planets will form, evolve, perhaps develop life, perhaps develop intelligence, and all of this will happen against the backdrop of the slowly unfolding transformation. And humanity, if it exists in any recognizable form, will not witness it. We will be gone long before even the earliest stages of the merger begin. Earth will be uninhabitable within 1 billion years due to the Sun's increasing luminosity. The Sun itself will eventually exhaust its nuclear fuel, expand into a red giant that may or may not engulf the Earth, and then collapse into a white dwarf. All of this will happen before the galaxies merge. So in a very real sense, this story isn't about us. It's about the universe, about processes that unfold on scales we can barely imagine, governed by laws we've worked hard to understand, proceeding without any regard for whether anyone is watching. And yet, here we are, watching, understanding. We've measured the motion of Andromeda across millions of light years. We've simulated the merger using the laws of gravity and hydrodynamics. We've watched similar mergers in distant galaxies and learned to read their stories. We've detected gravitational waves from merging black holes, both the stellar mass kind with LIGO and the supermassive kind with pulsar timing arrays. We've developed the mathematics and physics to understand violent relaxation, dynamical friction, starburst triggering, all the complex processes that govern how galaxies evolve. For a brief moment in cosmic history, there exist observers on a small planet orbiting an average star in an ordinary galaxy who can look outward and understand, at least in broad strokes, the fate that might await their galaxy billions of years hence. We can map the trajectories, run the simulations, make the predictions, and acknowledge the uncertainties. We can look at Andromeda and see not just a faint smudge of light, but a trillion-star galaxy on a possible collision course with our own. There's something profound in that, something worth pausing to appreciate. The universe is vast and old and mostly indifferent to us, but it's not incomprehensible. We've learned to read its story, and that story includes the eventual transformation or continued separation of our own galaxy. Whether the merger happens or not, whether we end up with Milky or with two galaxies that pass by each other and continue their separate existences, the universe will continue its grand evolution. Stars will be born and die. Planets will form and perhaps harbor life. Galaxies will continue their slow gravitational ballet, sometimes merging, sometimes passing by, always moving according to the inexorable logic of gravity and space-time. And somewhere, perhaps on worlds we cannot imagine, perhaps in forms we would not recognize, there might be observers looking up at their night sky and pondering the same questions we ponder. What is our place in this vast cosmos? How did we come to be? What fate awaits our world, our star, our galaxy? These questions seem to be written into the very nature of intelligence, the inevitable product of minds that can look beyond the immediate and contemplate deep time and cosmic space. We will not be here to see how the story of the Milky Way and Andromeda ends. But we are here now, in this moment, able to contemplate it, able to appreciate both the magnitude of the cosmos and our own improbable existence within it. We are patterns of matter and energy, organized in such a way that we can reflect on our own existence and our place in the universe. We are, in a very literal sense, the universe becoming conscious of itself, at least in this tiny corner of space and time. The potential merger of the Milky Way and Andromeda, whether it happens in 7 billion years or never happens at all, is a reminder that everything changes, that nothing in the universe is permanent. Galaxies, those vast islands of stars that seem so eternal, are themselves temporary structures, forming, evolving, merging, dispersing on timescales of billions of years. Stars come and go, planets form and are destroyed. Even supermassive black holes will eventually, in the almost incomprehensibly distant future, evaporate through Hawking radiation. But that's not a cause for despair. It's simply the nature of reality. Change is the only constant. And in that change, in the great cycles of creation and destruction that play out across cosmic time, there is beauty and meaning. We are privileged to exist in a universe rich enough and complex enough to give rise to galaxies and stars and planets and life and consciousness. We are privileged to live in an era when we have the tools and knowledge to understand, at least partially, the cosmos we inhabit. So when you look up at the night sky and see that faint smudge of light that is Andromeda, remember that you are looking at another galaxy, a collection of hundreds of billions of stars, some perhaps with their own planets, perhaps with their own observers looking back at us. Remember that this galaxy is approaching us, that our two galaxies are bound together by gravity, that they might merge billions of years from now in a slow, spectacular transformation that will create something new. Or they might not, might pass by each other and continue their separate journeys through the cosmos. Either way, the story is extraordinary. Either way, we are part of something vast and ancient and ongoing, a universe that never stops evolving, never stops creating new structures and new possibilities. And that sense of connection to the cosmos, that understanding of our place in the grand scheme of things, is perhaps the greatest gift that astronomy and science can give us. We are small, yes, limited in space and time, but we are also part of this magnificent, evolving universe, made of the same stuff as stars and galaxies, subject to the same physical laws, participating in the same cosmic story. The Milky Way and Andromeda, whether they merge or not, will continue their journey through space-time. And we, or our descendants, or whatever forms consciousness takes in the far future, will continue to look up in wonder and try to understand. If you found this journey through deep time and cosmic space meaningful, if it's helped you see the night sky with new eyes and appreciate the grand dance of galaxies, I would be grateful if you would consider liking this video. Your support helps me create more explorations of the cosmos, more opportunities to contemplate the profound and beautiful universe we inhabit. And if you'd like to join me for more voyages through space and time, more investigations of the questions that define our place in the universe, please consider subscribing. For now, let the thoughts settle. Let the vast scales of time and space wash over you. We live in a dynamic, evolving cosmos, and we are privileged to witness it, to understand it, however briefly. The galaxies will continue their dance, the stars will shine, and the universe will unfold according to its own grand logic. Patient and inexorable and utterly magnificent. Rest well, knowing that you are part of something vast and ancient and ongoing. The cosmos continues its eternal evolution, and for this moment, at least, we are here to witness it.